Professor Sergei Gukov came all the way from Caltech, from California, for one day to talk to you because he was intrigued by your curiosity. And he's going back late tonight after our party, and he talks in the later conference, the research conference, he will do by Zoom. So thank you very much for coming, and we want to understand how braids and machine learning, which is such a hot topic now, are connected.
Well, thank you very much for having me here, and it's a great pleasure to come and talk to you. So I didn't really prepare any words of wisdom to share, so I'll improvise. I definitely want to follow on what Mina said just before the break, that we actually like to be bothered, so it would be my privilege and honor if you reach out to me or other professors. That's why we're here, and that's how exchange of ideas happens. And maybe if there is any other piece of advice I should share from my own upbringing, I guess one of the most useful pieces of advice I got, which is kind of relevant to the subject I'm going to talk about, is from Sir Michael Atiyeh. So he was a great mathematician. And when I was young, I used to visit him pretty much every year. We would sit down, talk for a week together. And especially in his company, I thought that I should be very proper in a traditional mathematical sense. And I remember one day I said, okay, let's look at this problem through the eyes of, and then I was trying to switch topics, say, from algebra to geometry, this kind of transition that came up already here several times. And he said, Sergei, stop. Don't think about it as in terms of algebra or geometry. Transcend the boundaries. I mean, this is not important. It's all part of the same subject, and we're here to unify it. And to me personally, this was very liberating because I thought that, oh, each field operates by its own rules and people don't even talk to each other. But actually, that's not true. And one thing I learned, and this is the piece of advice I want to share with you, is that it's totally fine to cross the boundaries. And back then, this was many, many years ago, I couldn't imagine myself being on this stage talking to you about mathematics and machine learning. So this is another form of transcending boundaries. And I guess main message of this talk is that it's totally fine. It's okay. In fact, I have a confession to make that 3 years ago, I had no idea how to code in Python. I had no idea what machine learning is. But it's a very fast changing field and subject. And it's actually fun. So it's easy to play with. And what things I'm going to tell you about is basically a modern day version of a pocket calculator. When I was growing up, I started doodling with a pocket calculator and trying to multiply things, write simple codes, and so on, if it had some programming capabilities. So this is very easy to play with. And I didn't realize that you can go home and overnight achieve something that's meaningful, that's a result, and it's extremely easy. So one of the punchlines in the story is to explain why is this happening, what is happening now, and also I didn't believe 3 years ago that any of this could be useful for fundamental science. I was actually skeptical, so I'll be completely honest. I thought that what I do in my day job, say, proving theorems or developing some theories and so on, is so abstract that these modern-day pocket calculators simply cannot reach. And again, the message today is that it actually can happen. So I'll tell you two stories. At first, they'll start as kind of separate stories. There will be mathematics of braids, that's one, and then there will be computer science or technology. And that will be a separate story. But then I hope you'll see that they converge and interact with each other in a very meaningful way. So that's exactly this transcending the borders and boundaries of different fields that I want to describe to you. So what you see here on the first slide is a conversation that happened exactly 50 years ago. So I'll start with a slow history. 50 years ago in 1971, this was conversation between a human and a machine. So this was one of the very first AI systems, and in professional terms, this is called natural language processing or natural language understanding. So the goal of the computer was to understand what's happening, to interact with a human being in a meaningful way. And conversation is pretty reasonable. So here you can see, for example, person asking how many blocks are not in the box, 4 of them. And then there are various other questions. And it's a fairly meaningful conversation. You can see that this kind of conversation could easily happen between one person and another person. So machine is definitely following and conversing. But this conversation is about basically shapes of different color. So the universe of possibilities here is rather limited. So it's basically universe of different shapes in a box, and you can move them, you can rearrange them. And computer was doing this in real time, but still it's a fairly limited, but it's one of the first. And it was invented, or this machine was designed by this person. His name is Terry Winograd, and he is one of the founding fathers and the subject of natural language processing or understanding. It's basically how computers can converse with us, how they can understand the meaning beyond just a sequence of zeros and ones. So he is author of many interesting books. And by the way, the name of that machine I showed you on a previous slide is this. You can Google and figure out what these letters mean. So that's kind of homework project. So this is back in 1971. At that time when he devised this machine, he was in Cambridge at MIT. And soon after, fast forward maybe 20-something years, he moves to Stanford, to Palo Alto. He had many successful students. So this is one of them, one of the students who, even as a graduate student at Stanford, came up with a very nice, interesting algorithm how to order pages in search engines. Now we call it PageRank. Can you guess who the student is?
Probably from them.
Yes, that's co-founder of Google, Larry Page. So PageRank is named after him. And Google will show up several times in my talk. This is not advertisement to them. It just happens that certain results I'll try to quote from there. So, and the name of Terry Winograd, his advisor, whom I showed you, will also come up a couple of times. So I come from Caltech, and at Caltech, legacy of Richard Feynman is still very strong, and Feynman described here a process of doing fundamental science, and he compared it, so this was many, many years ago, again, back in the 80s, to sort of observing how gods play the game of chess, and we don't know the rules. But we see how the pieces move, and our job is to figure out what the rules are just by seeing the pieces on a chessboard moving. So I think this is a very accurate description, and if you think about it, this is actually how we learn things. And even in the previous talk, you saw that to learn something, what's the natural process? Well, we observe certain pattern. We try to make a conjecture. It's extremely important to test the conjecture. In a sense, it's extremely important to let ourselves make some mistakes. Because by allowing ourselves to make mistakes, we can clearly separate right from wrong and test various theories or conjectures and so on. So this is basically what Mr. Feynman is telling us here. And this is indeed essence of any learning process, especially learning fundamental science. So like I said in the beginning, I'll start with two stories. One is about fundamental science, in particular in this case, pure mathematics. And the other side will be some sort of technology or computer science. So speaking of chess boards and how we learn to play chess, also from experience. Here is chess grandmaster, Garry Kasparov. I myself grew up in Moscow, and as a young kid interested in mathematics, naturally, I was drawn to a club, chess club, organized in Moscow by Garry Kasparov. Huh? Well, my path is 57 and 54, but yes, number 2 is one of these, so I participated in some clubs too. Yes, so that's right. And yeah, this was shortly just before 92, where this picture is taken. As you can see, Garry Kasparov is extremely happy, relaxed, and smiling. Not so much in 96. So this picture 4 years after is taken from his first match between a person, namely Garry, and a machine. This is IBM's Deep Blue. So this is not machine learning yet. This is just normal computer. And well, you see, Garry Kasparov is already quite seriously struggling. And next year, in 97, he lost. So this match he actually won. It was close to a tie. But next year, in 97, he lost, and that's it. It's gone. So machines beat us in games of chess extremely well, up to...
One time out of 1,000, but what is the real situation now?
That's right. So that's what I'm going to tell you. So the real situation is, you're absolutely right. So this was basically the turning point, the way I presented here, and from then on, machines do better and better, and our kind of skills as humans stays roughly constant. So there is a more advanced version of game of chess, which is sometimes called Asian chess, the game of Go. And fast forward another 20 years, 2015. So I'll put this on the board because this is now closer to our time and closer to our subject. Something else happens. And now AlphaGo, designed by Google, beats best human player in Asian chess, in AlphaGo. And again, since 1997 all the way to 2000s, there is constant and very, very fast progress in computer technology. So computers can actually solve problems really well, way beyond what we can do as humans. Now, AlphaGo is probably the most complicated, the most advanced game. It has 10 to the 170 board positions, which is way beyond number of atoms in the universe. So 10 to the 170 is how many board positions you can meaningfully have in the game of Go, and number of atoms in the universe is only this. So it's much, much smaller. So first question then is, how can something that's built of atoms get reasonably close to analyzing this many positions? So that sounds pretty amazing, that you don't even have enough atoms to encode this information. So what's going on? And how do they learn? So these computers and AI systems that I'm going to talk about, they learn from experience. The basic principle is very simple. They do many trials and errors, and I think to us humans that's a great reminder that something that we do as children, namely trying something and falling and failing, is totally okay, because that's exactly what's stretching our boundaries of what we can and cannot do. And then they identify patterns and do exactly what we've already seen in other talks, including the previous one. They try to make patterns, make conjectures, and they become stronger and stronger. In fact, this is how chess grandmasters, such as Garry Kasparov, learn to play chess. So those of you who like books by, say, Malcolm Gladwell, he recently popularized this term of 10,000 hours, where he tries to explain that if you want to become professional more or less in any field, brain surgeon or violin player or mathematician, you have to devote a lot of time so that you see forest for the trees, so that you can recognize patterns, and once you're presented with something, it becomes familiar to you. But the way this process happens is through investing 10,000 of hours, or roughly 10 years in a given profession, to actually familiarize yourself so that things don't look foreign anymore. So, in particular, if Garry Kasparov looks at this chessboard, he immediately sees a very rich story. If, as a young kid, I didn't play chess very well in school, I have a look at this board, I see nothing. I see pieces and their random positions, so it's not clear what's going on. But to him, it is a rich story, and that's precisely because he already had many experiences, and he can quickly separate essential things from non-essential things, and so on. So what I'm going to do in this talk is replace the game of chess by yet another game, which has to do with braids, but I'll start with something that you've already seen before with knots. So this is a picture of a knot. Basically, it's a string, a loop, knotted together, knotted in some closed loop. And the question throughout this entire talk will be to tell if this is a trivially knotted string or non-trivially knotted string. In other words, can we, without cutting it or tearing it apart, transform it into a simple circle. And here in this picture, you can see that you actually can. For example, you can easily undo this loop, and you can bring this under, and so on and so forth. And this quickly becomes what mathematicians call unknot, a single unknotted string. And here, this picture is something that you and I can analyze within a few minutes. It's not so complicated. And analog of this game of chess will be to do it efficiently with much more complicated combinations. Instead of chessboard, we're going to use this string, this problem. So here is a more interesting example. And can you tell whether it's knotted or not? It's yes or no. So therefore, I ask you to vote yes for either one. So for instance, who thinks that this is a non-trivial knot? Who thinks it's a trivial knot, namely unknot? Yeah, it's yes or no. So that trivial. No, that's correct. Yeah. So it's a trivial knot. Indeed, you can undo it. So here is another example. Just guess. We have nothing to gain or lose. Unfortunately, I don't have candy to give. If I had, I would. So who thinks that this is a trivial knot? Who thinks it's untrivial, non-trivial knot? Okay, again, majority of you is right. This is non-trivial knot. And you see what's going on. It's just like with combinations of pieces on a chessboard, it gets progressively harder as you increase this number of so-called crossings or intersections. And this is a kind of problem that actually, if you think about it, is very amenable to computer science, because what's so special about all these numbers and AlphaGo and so on is that computers are really good with problems which have very short list of rules. The rules are simple, but space of possibilities, number of different combinations is huge. That's really what computers are good at. And this example of studying knots in topology, which is pure mathematics, has nothing to do with computer science, is actually exactly of the same type. This is to show that problems of guessing whether a knot is trivial or not is actually deep mathematically. So this is just one example of a paper where four very smart people, topologists, try to answer pretty much the same question as I asked you a moment ago. Can you tell whether a knot is trivial or not? And implication of this would be settling so-called smooth Poincare conjecture in dimension 4. So Clay Mathematics Institute in 2000, at the turn of the millennium, published 7 problems. One of them was Poincare conjecture in dimension 3, and now one of the biggest unsolved problems in low-dimensional topology is the 4-dimensional version, which is much harder. We don't even have a guess if it's true or not, so I guess if you try to ask audience of mathematicians or topologists, opinions would be split. Some would say it's false, some would say it's true. It's a very big problem. And if you look under the hood, what it reduces to, it actually reduces to telling whether knotted diagrams like this are knotted or unknotted. What's the catch? The catch is that real diagrams that we need to understand for smooth Poincare conjecture involve 170 crossings. I think this is the simplest example from the paper. And then number of crossings is 200, 400, and so on. So this is not something you can easily analyze with the naked eye. You have to have either strong mathematical tools or some other tools to solve this. So what separates us from smooth Poincare conjecture in dimension 4, again, this is very serious math, is complexity of such diagrams. So, but question is very simple. Tell me if it's knotted or not. And as Kurt Reidemeister taught us many years ago, the rules here are very simple. So there are only 3 basic rules. This is much easier than the game of chess. In the game of chess, you have to learn how pawn moves, how bishop moves, and so on. Here, very simple. You can move different strands in these ways. Every knotted diagram or piece of a braid can be related by just 3 moves. This is much easier than AlphaGo. And all we're discussing then is different configurations with only 3 rules. This is perfect for computer science. This is perfect for computers because rules are very concrete, very short list of rules, but space of possibilities is enormous. So, sounds good, right? So anyway, that's motivation. That's how we should probably try to solve it with computers and proceed. So before we teach this problem to a computer, something else happens, and this is where braids come in. Of course, you can try to show computer a picture, but this is a very bad way of encoding the information. Simply because most of the picture is actually irrelevant to topology, and as previous speaker emphasized, size or precise shape doesn't matter. What matters is what happens in these little crossings. And if I try to put a JPEG or GIF file to computer, it will spend most of its memory and attention on something that's not even important. But what's important is these little crossings. And what helps to emphasize this information is encoding of this knotted diagram in terms of the braid presentation. So here we have a braid on the left, and every knot can be obtained by closing the braid. So this is something that maybe you've heard yesterday, or maybe you'll hear more about today, but I want to include this for completeness. Is this clear? By the way, feel free to interrupt me at any point. I want this to be a conversation. So feel free to ask questions.
Sergei, are there finitely many diagrams that have to be checked?
Oh, you mean with SPC4?
Yes.
Yeah, so this is a very good question about history of smooth Poincare conjecture. So mathematicians, we want to solve this problem. That's what's keeps up at night. And there are constantly counterexamples. So there are many counterexamples being proposed. Some of them were settled later. Typically, what happens is that we as humans produce fairly limited families of counterexamples, potential counterexamples. And we are even worse at settling them, unfortunately. So yeah, that's partly why the community of experts would be totally split. We don't know if it's false or true. So if computers actually enter the game, they could help us in both ways. First of all, generating counterexamples. So we need some generative algorithms and models. And then also telling whether a given knotted diagram would be true or false to Poincare conjecture. So the paper I showed by Mike Friedman and collaborators deals with several famous potential counterexamples. And again, my main point there is that the smallest ones involve roughly hundreds of crossings, 200, 300 crossings. So this is really something we cannot address by any other means. Yeah.
You mind going to the previous slide?
Yeah.
Just to explain the details, because this is also connected to braid monodrome, even though I won't explain why. But you can see the first one, how the twist, you just twist it like that and it becomes simple. And the other one, you move the curve. And the last one, you also slide the line from one side to the other. It's still the 3 separate crossings here and 3 separate crossings here. The line was below, so the line could go below the other one. So these are 3 fundamental changes that are in braid monodromy also, and you can find these changes that Leonardo drawing. Okay.
Yeah, so these are the moves, now naturally called Reidemeister moves, that intuitively we understand is something we can definitely do with a piece of rope. But what's interesting is that theorem says that this is all you need to relate basically any knot which is topologically equivalent to any other knot. Yes, that's basically what it is. So that's right. So more proper mathematical terms here could be, there are actually several, and I have an extra slide prepared in the end. Maybe I'll comment about that. But there are several paths. So one is interpreting these diagrams directly as Kirby diagrams. Another, so this basically represents attaching circles for handles and building the 4 manifold or 4-dimensional ball. There is a relative version of smooth Poincare conjecture, which is of the same complexity. Another closely related question is to decide whether the knot, given knot is slice. So that's not exactly treating it as a Kirby diagram, but complexity-wise, it's again close candidate or counterpart, and there are various relations between these questions involving slice ribbon conjecture and so on. Right, so going back to a simple question, can we tell if knotted diagram is a trivial knot or non-trivial knot? So we see that it's hard, and we see that a useful way to encode it is in terms of braid. So from every braid, you can just add additional arcs and produce a knot, or maybe a knot with several components, which would be called a link, but that's also fine. So analog of this basic moves is as follows. First of all, you can encode every passing of a braid over or under each other in terms of what I'll call a letter. And letter will be sigma, it's just a random choice. Sigma 1 will mean that first pair of braids is passing over or under. So if I write sigma, it's one type of crossing. If I write its inverse, it's going to be the other type of crossing. So another letter will be, for example, sigma 2, that's about next pair of strands. Its inverse will be a different type of crossing. So this gives us a way to encode what's happening in the trivial braid, which corresponds to just strands running parallel. So this represents now operations of crossing like this. Okay? Very much like with Reidemeister moves, in this language of braid letters or words, there are equivalence relations. And again, there are very few of them. So if you try to read this braid diagram from top to bottom or the other way around, if the crossings happen far from each other, namely this pair and this pair get braided, so these are the words that we hear a lot during this weekend, then it doesn't matter in which sequence, in which order this happens. You can just, more interesting, which is analog of what we saw as Reidemeister 3 move, that's the non-trivial one, is this one, which allows 3 braids to interact in a meaningful way. And that's actually the only interesting rule. So again, same thing, not surprisingly, because knots are obtained by closing braids, we can reduce everything to the language of braids. And the possibilities are enormous, because we can write any string, any word or sentence in terms of these sigmas, but the rules are extremely simple. There are basically a couple of rules to think of. It's much easier to me than English grammar or any other language. And voila, if you have this set of rules and possibilities, you can encode any knot or any knotted diagram. So this is actually the smart way to feed the data to a computer, which actually encodes passing and braiding rather than the actual picture. So this is an illustration where you go from topology or geometry to algebra to speak to a computer. So computer actually likes algebra because it likes zeros and ones and basic operations. So this was story of math, and again, story of braids that you'll see in different forms throughout this weekend. And that's exactly what we tried with my colleagues. So the rest of what I'm going to tell you is actually based on joint work with my friends, Jim Halverson, Fabian Ruel, and Piotr Sukowski, where we tried to feed this string of sigmas or braid words into machine and ask machine to tell us if it represents a trivial word, namely if it can represent a trivial braid or not. So sounds very simple and sounds perfect for machines that like huge possibilities out of basic simple rules. Now, you already probably start seeing why I showed picture of Terry Winograd on the first slide and first example of early AI system that tries to communicate with human and understand the language. See, even when we speak about braids, we mention things like braid words. So we think of braid words as words. So this is an example of a language in which letters or words are made out of braiding. And different sequences of the sigmas of braid words encode different braids, different knots. So therefore, the question I'm asking is that in this particular language, in this mathematical language of braids, can I recognize if a very long sentence is trivial or non-trivial? That's all I'm asking. So that's why some technology that tells us how to interpret and understand language could be extremely useful. So now let's dive a little deeper into this other story, parallel story of natural language processing and natural language understanding. Way before serious computers or AlphaGo type machines were developed, Terry Winograd proposed that for computers, future computers at the time, it would be useful to have stress tests. Remember, I told you that it's important to allow ourselves to fail, to know where the boundaries are, so we can actually go further to stretch these boundaries, make technology better or stronger. So he proposed what computer scientists call Winograd schemas. These are very tricky examples, naughty examples, if I may use this pun, for machines who want to translate sentence, for example, from one language to another language. And he proposed sentences which are tricky because we as human, from the context, can clearly understand what is happening, but it's important to achieve the same for a machine. For instance, let's look at this example. One of the Winograd schemas is that the sentence, the trophy would not fit in the brown suitcase because it was too big. Well, you can also replace this with small. And if I ask you, what was too big, is it a trophy or a suitcase? You probably see very clearly that the trophy is too big, that's why it didn't fit. So we figure this out from the meaning of the sentence. Now, why is this important? Why did he care? He cares because if you want computer to do accurate translation, for example, or understand the meaning of the sentence and translate it into some other language, in another language such as French or German, the nouns, trophy and suitcase may have different gender. So if we are to do it accurately, we have to know the context. So a machine has to know somehow that it was the trophy that was too big, and that's why it didn't fit in the suitcase, and so on and so forth. So here is another example. So I told you that 2015 is kind of a number to which I'm going to return several times. And without giving a few full course on machine translation, so you can find many of these courses online, including on Stanford website and various other places. History is such that in 90s and 2000s, early 2000s, the way machine translation worked was very probabilistic. So it read a bunch of books, again, it learned from experiences, and then created a probability matrix that certain words fit together, or when translation happens, for example, typical parallel corpus that these machines use is actually Bible, because it's one of the sources that's widely available, has rich vocabulary translated in many languages. So it compares texts and learns from it and sees what typical sentence would look like in a different language. And this works reasonably well. So this is called statistical machine translation. So this is actually what Google used in early versions of Google Translate and many other versions, and it does reasonably well. So if you build a big enough statistical probabilistic model, it performs reasonably well. So this vertical axis is so-called blue score. If you speak several different languages, you probably would be around 30 if you're very fluent in both languages. And as you can see, this machine translation is not too far from this level. So it's doing pretty well. And every machine translation actually has roughly two parts. So one part is trying to encode the information of the source. It's called translation model. And the other is trying to generate the sentence in another language. That's the language model. So what happens is that you first have to understand the meaning of the sentence, encode it in terms of zeros and ones, feed it to another part of the system that tries to generate now text out of meaning in a different language. So this is very typical. It's completely standard, and it's going to be true in many different types of algorithms that I'll try to survey in this talk. It's, again, very general. It works in any version of Google Translate or another translator or other programs such as parsing sentences that you can encounter. And again, you can see here on this graph, same phenomenon to which I tried to draw your attention in the beginning, that a few years ago, it's actually fairly recent, it's happening now, something happened, something changed, and another type of algorithms called neural machine translation, this is based on artificial intelligence, surpassed statistical machine translation. This is where we use neural nets for this process, and their performance basically skyrocketed. So what happened is that the first paper on neural machine translation was published in 2014, and already in 2016, Google completely replaced its previous version of statistical machine translation with this neural net version. So everything was happening very fast. And now that's why it's kind of a revolution in artificial intelligence, machine learning, and the aspect I'm describing for you related to the braids, because we want to understand braid words, braid translation, is natural language processing aspect of it. So how does it work? This is, again, not a course in computer science, but I don't want to be too shallow in this talk and just review history. I want to show actually a little bit of principles that allow these things to work. So you have a sentence in one language, and you want to translate it into a different language. So my original sentence is going to be, you asked us to call you back after last Friday. Okay? So this is an actual example. What happens is that in early versions of these translation models, again, they all have two parts. One is encoder, the other is decoder, or language model and translation model. They call it slightly differently in different contexts. So typical thing which existed in around 2015, I guess, is so-called sequence-to-sequence architecture, where you take one sequence, step by step, you take every word, you encode it, and then you pass this meaning vector to another part of the system, which step by step is trying to undecode it. So those of you who speak German realize that this is not a perfect translation at all. It says roughly, however, we hope you call us back with your travel plans or something like this. You come back to us with your travel reservation. This is not exactly what the English sentence says. Well, meaning is quite different. And things like that happen a lot, especially with these early translation models. Again, if you speak some of these languages, you can probably see how this happened. So yeah, sleep and fall down carefully, eating carpet strictly prohibited, and so on. So what's missing, of course, is that the meaning of the sentences gets lost in the translation when sometimes things are translated quite literally. And this was the issue with translating things step by step. And this is a typical thing because for such sequence-to-sequence encoders and decoders, it's really hard for a machine to keep the context over a long range of sentence, of the meaning. For us, since we're aiming for topology, it's going to be extremely important because the whole answer to the question, is the braid trivial or not, will change if I change one little detail somewhere. So therefore, it's extremely important to understand the entire thing very, very well. So a machine had to keep the context and understanding of the meaning over a long period of text. So that was the challenge in, I would say, 2015, 2016, and so on, when this was exploding. So something else happened around the same time. So people, smart people in computer science and machine learning came up with an idea which naturally is called attention. In fact, this first came from computer vision. And the timeline here was that in 2014, this idea was first circulated in computer vision, and 2015 was implemented and so on. And it's called attention mechanism. The idea is that aside from the sequence-to-sequence recording and decoding of information, you try to assign the weights and keep them separately. This is called attention. And then there is a particular way to basically weigh different parts of the sentence so that most important or meaningful parts of the sentence get higher weights, numerical weights. So this is called attention mechanism. And again, it was implemented in 2016, 2017, roughly speaking, and this is an example of another problem. This is not translation, but parsing the sentence, where you want to put a sentence as an input, and in that same language, you don't need to translate it. You want to reduce the sentence to, say, shorter version of that sentence, but of course, you want to keep the meaning. And here is an example of this attention metrics. These are these boxes, or strength of the color is exactly the weight, so it's telling you what's important, what's not important. So this is a visual representation of this attention mechanism, if you wish. And here is the input sentence. It's a very long sentence. Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism. And parsed sentence is, Russia calls for joint front against terrorism. Very good, actually. So that conveys the meaning. So words are different and so on, but that's fine. So this now works much better. It's much better than don't eat carpet, right, in the airport. Yeah? Yeah, so here I'm, of course, just conveying the basic idea. So I highly recommend, again, digging, for example, into one of the sources. This is extremely good question. And it goes back, in fact, even to statistical machine translation, where I'll illustrate kind of precursor of this, because again, in limited time I don't think I have capacity to explain the full idea, but maybe just a little glimpse into it. So even in statistical machine translation, how would you solve a potential problem of long-range dependencies? So one problem is that suppose you make a mistake somewhere in translating the sequence. If you're really trying to read it step by step, that's how any normal algorithm would do it. You may make a simple mistake, and then it potentially can deviate you on a completely wrong course in one of the sentences, don't eat carpet. So it's a good idea sometimes to keep several versions in a bank. So you translate several different, you keep recording of different options for translation. And then maybe a little further down the road, you realize that, oh, the option which was not favorable by probabilities in the beginning is now suddenly winning in the end. And the one which was preferred earlier now completely plummeted and is not favorable according to the probabilities that I see further down the translation. So this is a simple way, which in a way is kind of precursor to this attention mechanism of keeping several beans and recording additional information. So what's happening here is somewhat similar, but again, in a slightly different architecture. Any other questions? The formal answer that I didn't want to say is this formula here, which is on a slide, but then I have to decode who are the Q's, so-called key vectors, and the values, and anyway. That would take additional time. But it's not too complicated. It's all linear algebra in the end. Right, so then from Google Brain, you see Google research here in many places in 2017. Came out a very nice paper that was another mini revolution in this whole subject. So the idea of the paper was very simple. They said, throw away everything else in your code or computer that you had and keep only this part, the attention. So that's basically the title of the paper. This mechanism that assigns the weights. And well, yeah, and it worked. What's interesting, it worked amazingly well on so many other tasks way beyond machine translation. So that created a kind of mini revolution in machine learning. So I'm giving you, like I say, two stories. One is mathematical about Braids, and the other is about like a short history course on what machine learning is about, what kind of problems they solve. So see for yourself. So these are some of these schemas from Terry Winograd that I showed you. He invented as stress tests way before any serious machine learning techniques even existed. And some of them are pretty cool. For example, the cow ate hay because it was delicious. And if I ask you to answer who was delicious, the cow or the hay, you would immediately answer. Why is it important? Because if we translate it in this case into French, we have to know the gender. And we don't want to make up gender. We don't want to make such mistakes. We want to be careful about it. So as you can see, the previous version of Google Translate, this is 2017, makes mistakes half the time. This transformer, that's the architecture based on this attention mechanism, is pretty good. Does much better. Well, there is, this is to illustrate that I told you there are two parts of the machine. One is encoding the meaning, and the other is generating the text. So the second part, to which I paid a little less attention so far, is something that can predict what the next words are. And it can be so good, if you train it really well, from a single word, it can actually generate the whole Wikipedia page. So this is an example from Lukasz Kaiser of a trained neural net. Neural net trained, meaning it saw zillions of Wikipedia pages. And they gave it only one word, transformer, because this was the name of this architecture that they devised on the attention mechanism. And they asked machine to generate a Wikipedia page just out of a single word. So, of course, if you run it today, it may generate one piece of text. If you do it tomorrow, it may be another piece of text, but it's always coherent, and it always follows more or less the style of Wikipedia pages. So in this particular run, on one day, it generated a text assuming that Transformer is a Japanese rock band, if I'm not mistaken. And then it follows the history. It says that band formed, then guitar player left, and band disappeared, then it's based on such and such style of music. So all of this is made up. I mean, band doesn't exist. But if I ask you to read this text and tell whether it's true or not, it's really hard to tell. It's pretty good. It's, of course, grammatically correct, and it follows all the typical layouts of the band history, so it knows that it's talking not about car makers, but rather music and band, and all the right ingredients are already in here. So this is...
It's more a statement about Wikipedia than a statement about machine learning.
Well, both, I guess. What machine had to do, it read through zillions of Wikipedia pages, and it learned, just like Garry Kasparov and every other instance of vast amount of information, it processed it, it found patterns, and now it's able to generate patterns. So now this is illustrating how the second component in machine translation works. If you give it a meaning vector, for instance, it surely won't make a mistake. So here it did it perfectly just from one word. So you can imagine how it does if you really try to tell it the meaning that, say in one language that we're talking about such and such thing, of course it will do pretty well. Anyway, so this is the last stop in my tour of different architectures, as they're called, of machine systems. It's basically to say that there is, when we're doing this, that's the last word as of 2020. It's a fancy name called Reformer, basically advanced version of this transformer that uses some advanced techniques. And again, Google research pops up as a typical place where many of these things are done. This is an excellent. Now, without further ado, what would happen? So suppose you give this fancy attention mechanisms and reformers and transformers some of the braid words. You show them lots of braids which are trivial. You show them lots of braids which are non-trivial. And then you give an example which you ask to recognize. How well would it perform? So one interesting thing that happens here is that it actually performs better on more complicated braids. So if you give a braid,
So the human, you mean?
well, even compared to itself. So as human, we cannot go beyond, I would say, 15, 20 crossings. So that's typically where pure mathematics stops. So we don't have currently techniques. That's why smooth Poincare conjecture is so hard. Again, what separates us is complexity that we need is roughly 200 crossings. That's what I mentioned in the beginning of the talk. What we can do as mathematicians with analytical techniques is only 15 crossings. So we are at least one order of magnitude off, and probably more, because one order of magnitude will barely get us into the game. For computer, what's happening is that its percentage of correct answers approaches 100% very quickly, so you can train it more and more, and so this epochs is number of training cycles, and it quickly goes to 100%, and what's interesting is that the positions of red, green, and the blue lines are positions of training with braids of different sizes, roughly speaking. And what you see is that as number of crossings becomes higher and higher, it actually performs better. To me personally, this was counterintuitive because you give it more and more complicated examples. But I think, in retrospect, I don't have a full mathematical theorem for this, but analyzing what's happening under the hood, I think what's happening is that with more crossings, you have more possibilities. And you have more interesting possibilities. So basically, you're asking machine to play a high-level game, and it learns better. So that's, I think, what's going on. Yeah.
Is it possible that the unknots that you're feeding it, or the knots that you're feeding it, can be unknotted in many more different ways for those much larger knots?
Probably, that's also true, but a path to unknotting them, I guess, question is, what's the percentage of different paths that lead you to unknot? And that quickly diminishes, of course, with number of crossings. That's the difficult.
It doesn't only say yes, no, also give the list of moves.
Very good. So that's a very good question. So in artificial intelligence or this machine translation or learning, there are two types of machines. One, so here I'm showing you an example of a machine whose goal is to train and say yes or no. So it doesn't tell me how to get there. It's very good at predicting. It's very good at predicting. So
if you say that humans cannot do more than 15, how do you check it?
Exactly. So then, you find a very good topologist. I learned a lot from Bob Gomf, who played with this kind of examples. And you say, hey, this machine says it's a counterexample to smooth Poincare conjecture with probability 99.999. Can you go and check it? And he probably goes for a year in hiding and comes back with an answer. Of course, there is another type.
That's not what we expect you to do as a mathematician.
You can do this as a mathematician. But there is another, if you give me a little bit of time, I think I'm doing reasonably well. I'll show you another type of algorithms whose job is to actually do the unknotting. This is a much more active model. It's not just saying yes or no. It's really about finding the path to the unknot and doing it in practice. So that's much more useful, of course. So the reason I asked for a little bit of extra time, I think I was going a little slower, but again, if it's not too technical, if you allow me, I'll use 10 more minutes. Is it okay? Is it? If it's too hard, I can skip this part. This is the last part. So it's all fun, and I promised you 2 stories. I'm basically finished with 2 stories. One is mathematics, is machine learning, something again that 3 years ago I had no clue about. I'm completely honest, and I'm not very good with computers. I think if you are interested in this, you're gonna learn it much, much faster than me. So I'm a much more pure scientist at heart, but I enjoy this immensely because now on laptop I can do something meaningful in 1 hour, whereas when I try to prove a theorem, it takes me years, and this sounds much more rewarding. Anyway, there is another theory aspect to this whole story. Theory aspect has to do with complexity theory. So computer scientists invented this notion of how complicated a problem is. And on Clay's list of millennium problems, there is actually one which is right about this complexity theory, which is now part of very respectful mathematics. And the problem is to show or prove or disprove if P equals or not equal to NP. So what is it about? These are complexity classes, according to computer scientists. So this is an abstract or bonus story, if you wish, which says that some problems are easy. What does easy mean? You can solve them in polynomial time. In computer science, an algorithm in polynomial time means you can do it really fast. So the problem with these knots, as we're struggling, is probably that these are somewhat hard problems. So we're going to look into this in a second. Problems which are not so obvious are Sudoku type problems. So if you're given a Sudoku puzzle, you don't necessarily construct a quick algorithm to solve it, or at least we don't know one yet. But if you're given a solution, you can quickly verify that's a correct solution. So this problem is called NP, unlike P, which you can solve in polynomial time. It means that you can quickly check the answer in polynomial time, but you don't have an algorithm to solve it directly. So what Clay Math Institute is asking you or giving you $1 million for is to show if these complexity classes are the same. Namely, if all problems which you can quickly verify the answers to are also solvable, for them there is at least in principle an algorithm which can do it quickly. So this is P versus NP. Unlike a smooth Poincare conjecture, most people believe that these classes are different. So here there is a clear winner that community is definitely skewed in one way. So let's ask, how is our braid word problem? How does it fare in this, in this complexity scale. After all, I showed you this, and it seems to say that for a machine, this is an easy problem, right? I mean, that's what it's suggesting. So could it be that there is simply a polynomial algorithm? Well, these people, this is also fairly recent. So this started, again, in late 90s, but mostly in the past 20 years, showed that this unknotting problem is in complexity class NP. So it's kind of reasonably, not too easy, not too hard, so it's hard to say. But soon after, Greg Kuperberg and other people, I'll show you on the next slide, showed that it's also co-NP. So what it says is that this unknotting problem, now because it belongs to the intersection of NP and co-NP, what is it? It means that you can quickly check positive answer. You can also quickly check negative answer. And many problems, for example, such as deciding whether integer is a product of 2 prime, which historically started at the intersection of these two complexity classes, namely that you can quickly verify positive answers and you can quickly verify negative answers. Eventually, algorithms in pure polynomial time were constructed, so therefore, everything or many things that started in NP and co-NP ended up being in polynomial complexity class. So this is the Venn diagram, or one fantasy of Venn diagram for complexity classes. Again, because we don't know how they relate to each other, this is only a fantasy. We don't know if P is all of NP, probably not. That's why this rendering, I think, is quite accurate. But it shows you that if something is here in this intersection, it has a good chance to be in P. So this suggests, or this points us in a direction that this knottedness problem that we're trying to play these machines against is getting close to P. And this is another paper where the same theorem was proved without assuming generalized Riemann hypothesis, which was one of the assumptions on the previous slides. And interesting corollary of this is that if either of the decision problems in knot recognition and knottedness, this is precisely the negations of the problem that we're discussing, is NP complete, that's yet another complexity term or class, which means that every other NP problem can be reduced to it, then NP equals co-NP. So in complexity theory, this is another big outstanding question. We don't know if P equals NP, this is a clay problem, but we also don't know if NP equals co-NP. So in other words, is it always telling quickly identifying positive answers and negative answers, same thing? So we also don't know this. So in complexity theory, there are many cool things. And this seems to point in the direction that our problem is actually not too hard. But we shouldn't celebrate so early, because this problem of deciding whether some knotted diagram can be reduced to unknot or not is actually very close to the very hard problems in computer science and complexity theory. Why? Because it's about connectivity of a graph, so whose vertices are different knot diagrams, and such problems are notoriously hard. For example, traveling salesman problem is of this type. And this paper shows that if you put a bound on how many moves you're allowed to make, it immediately becomes NP hard. So it's one of the hardest things in this theory. And also, if you try to do it with various invariants, for example, there are many invariants of braids and knots that we could use that usually don't even work up to beyond 15 crossings. So some of you could have asked, why don't we just compute the Jones polynomial? Well, first of all, we cannot, because beyond 15 crossings, it becomes exponentially hard, and this is mathematical reason why, because it's in a class sharp P complete. This is much worse than NP hard. So it's just hard. So therefore, we're in an interesting situation where we had indication that the problem is not too difficult for a machine, but if you look a little closer, it actually is pretty difficult. So now I finally give the answer to the question of another neural net whose goal is to identify the path and actually tell how from a given diagram find whether it's knotted or not. So here you have to have some different architecture, and these are several examples. So RW, this green one, is random walker. So this is something that basically tries random moves and just shoots in the dark and in hopes of finding something. Of course it doesn't, so percentage or accuracy quickly drops to 0 as you increase the length of the braid or number of crossings. So shooting in the dark or just guessing the answer never got me far on the math test. So the one which performs really well is the blue one. So let's look at this algorithm or thing a little bit closer. So many machine learning techniques, at least in old days, typical neural net, the simplest would be called feed-forward neural net, is based on gradient descent. So it basically asks, in a given position where I am, what's the best place to go? And so on. And then makes a move. But then, this move, for example, if you're standing here and your direction is that way, and if you make a move, if it's a sufficiently big enough move, you may actually fall down the cliff and never recover. So that's the problem. In fact, that's exactly the problem with these braids. So kind of a following direction in a certain prescribed manner is somewhat dangerous. And what does this algorithm called TRPO does? Instead, this trust region policy optimization algorithm says, I'm standing here, I'm going to analyze points in my vicinity and make the best move within this radius. Then I'm going to repeat the process. So that's why it's called trust region policy optimization. And as you can see, it performs really well. This is, according to the braid complexity, this is not accuracy now, this is average number of steps. So this is related to one of the previous questions. If I increase the braid complexity, how many steps do I have to make it unknot? So we already know that this blue thing is performing really well, so it's finding unknots. And as you can see, everything else requires a lot of steps, and it's kind of getting slow. But this thing is moving reasonably well. And here at 100 crossings, it requires roughly 100 steps, which is reasonable. Yeah, same order of magnitude. Anyway, so this concludes it all, and I hope I conveyed the story that it's okay to merge two completely different worlds, again, worlds that 3 years ago I wouldn't have imagined talking in a very meaningful way. Thank you.